Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to try to describe a very important quantity in the study of electricity, electric potential. So after watching this video, hopefully you'll know how or what electric potential is, why it's important, and a little bit about how to calculate differences in potential. So before we talk about electric potential, I'd like to go back and talk about what's called gravitational potential first. Because I'm a big believer in, trying to use things that we already know about to try to learn about the new stuff. So here's, imagine this picture of me here, and I've got my coffee cup, and I'm standing next to, I don't know, some sort of hole in the ground. And let's just talk about that coffee cup for a moment, right? Ignore me, it's just all about the cup. The cup full of coffee here, I can calculate a potential energy for. Remember that gravitational potential energy is equal to mgh. Now, you measure the h relative to some chosen datum. And it's pretty typical to put datums on the ground. So I'm going to go ahead and put a datum right here on the ground here. So this line right here is going to be where I'm going to measure my potential energy from. So datum. So now, let's chat about that cup, and I'm going to kind of steal it from myself here. This cup now, if it were at the datum, basically anywhere along here, we would say its potential energy is 0. If it's up here somewhere, we would say its potential energy is some positive value, calculated by this equation. And then if it's down here, maybe in the well here, we would say its potential energy is some negative value, and again, calculated by this equation. So I'm just going to put this cup here. We're just going to let it kind of float in space here for a minute. Now, over on the right, I'm going to make a little algebraic substitution here. I'm going to say we're going to let this letter V here equal G times H. If I do that, all right, now our potential energy equation is M times V. Now, if you kind of study the units of this V, you'll notice, you could write the V as potential energy over mass. So this thing has units of joules per kilogram because potential energy is measured in joules and mass in kilograms. Let's talk about some numerical values too. And for the sake of this video, all right, gravitational acceleration or gravitational field strength is about 9.8 meter per second squared, or 9.8 newton per kilogram, depending on the unit. I'm going to write it as newton per kilogram. I'm going to just approximate that to 10 for the sake of this video here to make the math easy. Right? This quantity, your potential energy per unit mass, is called potential. It's related to potential energy. But it's not a potential energy itself. It has units of joule per kilogram, not joules. And this is how potential is calculated. And what that means is, pardon me, if I come up here about 1 meter in height, I'm going to go ahead and just draw, a green line here. If this is about 1 meter in height, that means that our potential here on this green line, darn it, that's what I wanted. Our potential at this location is about 10 joules per kilogram. And here's where I'm getting that from. G is about 10, and my height here is about 1. If we come up another meter, about here, give or take, now our potential, I'll write them over here, this is 10 joule per kilogram. Now our potential is about 20 joule per kilogram. And if we come up another meter, now our potential is about 30 joule per kilogram. Right? Now you'll notice that as I get higher and higher and higher, the potentials are getting higher and higher and higher. This line right here, we'd be at a potential of 0 because the height is 0. I could also come down here now, about a meter, and you can probably guess what the potential here is going to be. It's going to be about minus 10 joule per kilogram. And if we go down another meter, we're going to be at a potential of about minus 20 joule per kilogram. Now, some very important things to take note of. This, what I call a line, it's not really a line, it's a plane, because you got to imagine this coffee cup here. If it's anywhere along this line, it would be at a potential 10 joule per kilogram, but it also could come like at you. As long as it's 1 meter off the ground, the potential would be 10 joule per kilogram. These lines have special names. They're called equipotentials. And they're not lines at all. They're actually surfaces. They're horizontal surfaces. So these are all equipotentials. They're horizontal surfaces. And here's what the potentials tell us. Like this potential here, which is 10 joule per kilogram, what that means is if I put 1 kilogram of mass anywhere on this surface, it will have a potential energy of 10 joules. If I take that kilogram of mass, I move it up here, it will be at a potential energy of 20 joules, and so forth. So the potentials are telling us about potential energies. The coffee cup, right, if I move it anywhere horizontally or kind of at you or away from you watching this video, I'd be moving it along an equipotential. The potential is not changing. If the coffee cup moves up at all, it's moving towards higher potential. If it moves down, we're moving towards lower potential. Also notice an important fact here, the gravitational fields are down everywhere in this picture, and they're uniform. Notice that the cup, okay, if we move up in the opposite direction of G, we're moving towards higher potential. If we move down, we're moving towards lower potential. If we move left or right in this picture, we're not changing in potential. So it's very important to realize you only change in potential when you move with the field. If you go down with the field, you're dropping in potential. Against the field, you're increasing in potential. And what the potential tells you is it tells you the potential energy per unit mass. So it's related to the mass, or I'm sorry, it's related to the potential energy of the system. Or I should say it would be used to calculate the potential energy of a system. Now remember though that the potential energy depended on the datum. Well, the potential also depends on the datum. You can call zero potential anywhere you wanted to. If I were to move the zero here, the ground would now be at a potential of 20 joule per kilogram, and this would be 40 joule per kilogram, and this one 50 joule per kilogram, and so forth. If I put the datum here, this one would be negative 10 joule per kilogram, negative 20, negative 30, negative 40, negative 50, and so forth. The only thing that ever matters are differences in potential. If I drop that cup from here to, and it falls and hits this well, now right here we're not quite a full meter down. Let's say this is about minus 25 joule per kilogram. So if I drop that cup from say this location, it's going to change in potential by 10, 20, 30, and another 5. It's going to drop in potential by about 35 joule per kilogram, and that's going to be true no matter where we put the datum. All right, so gravitational potential, here's how it's actually defined. Potential energy per unit mass. What does it tell you? Well, it tells you how much potential energy any given mass would have at any of these locations. So for example, this 10 joule per kilogram equipotential, what that means is I put an object here, it will have 10 joules of potential energy for each kilogram of mass, right? It's relative to some datum, which is perfectly fine. You can put a datum anywhere you want, and basically potential is used to calculate potential energy terms. Now, very important point though, again, in this picture, anytime you move down, you will drop in potential. Anytime you move up, you will increase in potential. Anytime you move left or right, there'll be no change in potential. You only change in potential when you move with or against the field. All right? So now let's get to electric potential. All right, so we're going to imagine in this picture that we've got a nice uniform electric field that points to the right. And again, we're going to imagine it's uniform, and I'm going to try to describe that with, I use these, some electric field lines. So hopefully you've seen my video on electric field lines. These are just ways of kind of visualizing electric fields. If the electric field is uniform, we would have, the spacing would stay constant. All right, so we're going to imagine this region in space where we have this uniform electric field. Now, the value of it doesn't matter. If I put a charged particle here with a positive charge, this particle would feel a force, and that force would be to the right. Now, this particle, if allowed to accelerate, right, it's going to accelerate because there's a force equal to charge, whatever the charge is, times this thing's electric field strength. If we imagine this particle accelerating to the right, this force is doing work, and the kinetic energy of this object would go up. We can define a potential energy for this force because this force is a conservative type of force. Now, I'm going to save that reason for another video because I don't want this to get too long. For now, I'm just going to ask you to take my word for it. We can define a potential energy for this force, and that potential energy is going to be the same anywhere along this path. Right? Now, I'm going to draw a datum here and call this potential energy 0. If we say that the potential energy of this object is 0 anywhere, anytime it's on this line, that means that here it's going to have a positive potential energy, here it would have a 0 potential energy, here it would have a negative potential energy. Moving this way isn't going to change the potential energy because of the direction of the force. If you look at the work done by this force as this moves from here to here, I'm going to call this distance, let's say, x. The work done by that force is equal to the force, charge, times the electric field, times the distance x. And that work term is going to be positive as this object moves from here to here. Now, I'm skipping some of the math detail. For now, I'm just going to explain it like this. This work term is a potential energy. The potential energy, then, of this particle at this location can be described by this equation. Charge times the electric field strength times x, where we're measuring x from this datum. Anytime this object's on the left, we would say the potential energy is positive. Anytime this object is here, we'd say it's 0. And when it's over here, we'd say the potential energy is now negative. Now, similar to what I did earlier, where I said, when we were talking about gravitational potential, and again, earlier, you remember I said, let's let V equal G times H. Previously in the video, I'm going to do a similar thing here. Notice this is field strength times distance. Now I'm going to let this V equal the field strength times the distance. And we can rewrite this term, potential energy equals charge times this big V here. Now if you solve this for the capital V, we get potential energy over charge. This quantity that has units of joules per coulomb, this is what's called electric potential. I'll just put EP here. That's what electric potential is. It's defined as potential energy per unit charge. The potential would be constant anywhere along this surface here. And again, it's a surface. It's up and down, but it's also kind of at you and away from you. You'd only change in potential if you move right or left in my picture. So this line right here, this surface, is an equipotential. If I go ahead and draw a couple more of them, I'll draw one here. This would be another equipotential. Oops, I'm drawing these in green. This would be another equipotential. Right, and this one over here, another one. And again, the intention here was that these lines keep going and going and going. Let me draw one more. Right, so, and I'm going to give these numbers here. Let's call this one like potential 1, potential 2, potential 3, potential 4, which we've set to 0, potential 5. Right? So when we look at this picture, we have electric field lines, and they're pointing left to right. I should have actually had arrows on these two as well, but and I now have equipotentials represented by the greens here, and these are actually surfaces. In this picture, you would change in potential anytime you move to the right. In fact, anytime you move to the right, you'd be dropping in potential. So of these numbers, the highest potential is this one, because you always drop in potential when you go with the field. The lowest potential in my picture here is this one. So anytime we move to the right, we're dropping in potential. Anytime we move to the left, we're increasing in potential. Anytime in this picture we move up or down, we are not changing in potential. All right? And I think that's probably enough for this video. Let me just kind of summarize it like this. Here, what is electric potential? It's potential energy per unit charge, and so therefore it has units of joule per coulomb. 1 joule per coulomb, by the way, has its own special name. It's called 1 volt. Okay? Why is it so important? Well, potential is related to potential energy. All right, so it tells you something about the behavior of particles in this region. And it's used for problems in dynamics, like writing work energy theorem stuff, and we're going to talk later in the course about how potential is related to drive charge through circuits. Another important fact of life about potential, you have what are called equipotentials, like I have drawn. This is what they would look like in this particular field configuration. I'll save other configurations for another video. Very important fact of life, you drop in potential anytime you go with the field. If you go with it, you drop in potential. You go against it, you increase in potential. If you go right angle to the field, no change in potential. You can look at this equation here and kind of guess how potential differences are calculated, but again, I think I'll just save that, the details of that for another video. So, all right, I hope this video helps describe what electric potential is. Have a great day.